All right, so today we're going to continue with the asymptotic analysis. But before that, let's see what's to be reminded. Your assignment number 1 is due next Monday, so please check the precise time on the instruction PDF. And if you got any trouble, reach out to me. I still got office hour today, this afternoon, 3 p.m. in the office. Or you can reach out to the TA, find their information on the eClass site. And the split array harder. The split array harder is going to be very beneficial for you to try it out, and I will release the solution a little bit later. Do give a try. It's really going to help you improve the recursive thinking for programming test number 1. All right, reach out to me if you need any discussion or hints about that. Any question? All right, let's now do some recap about last time, and then we'll continue. All right, so last time we actually talked about this very important concept about going or making a transition from absolute running time into relative running time. I think that you guys should spend time convincing yourself you haven't been yet. So it's very important to know. The conclusion is, given the T over here, which is the exact execution time depending on the platform, we can simply safely disregard it for our analysis purpose. Either you got the same algorithm on the same on different platform, or you got different algorithm on the same platform. For both cases, you can safely disregard the value of t, right? We can just compare just the runtime function to make a decision, whichever that's going to be more efficient, right? So that's the main conclusion you want to watch out for. And then we talk about approximating the runtime function here. For example, there's one example here. And the principle is you want to, first of all, identify the highest power. Once you have done that, you can safely drop all the lower terms and also drop the multiplicative constant for the highest term. And then you will get, for example, approximation n squared. And this will be a very nice way to really get usually the part 1 answer to see. I give you a runtime function there. I ask you to decide the asymptotic upper bound. So this will be a very nice way to guess or to derive the answer first. And part 2 will be to formally prove it, which I'll get into. We'll do lots of examples today. And then we talk about this graph here, which is very important. We're still going to revisit this graph when we talk about defining big O like a family concept. So you really need this diagram as well to make some relation, right? I'll talk about it. But just identify all the common runtime function here. So these are more or less what you run into mostly for the algorithm, even in 3101 would be very common. So what you really want to watch out for is, ask yourself, if I am given any arbitrary 2 functions over here, let's say function number 1, function number 2, which one grows faster asymptotically? Apparently this one grows faster. That means it's less efficient. Asymptotically, it's going to take more time than function number 2 to complete. All right, so that's some principle you want to remember, but we'll reinforce this very soon today. We're going to talk about some nice properties about big O, very practical properties that you also want to keep in mind. And we did exercise over here just about how to approximate the running time. I discussed the principles already, but you guys can review this example. Pretty straightforward. Okay. And then we spoke about the formal definition for big O. I'm not going to repeat too much. You guys can see the recording or reach out to me if you want to discuss the actual definition. But today, I want you guys to, maybe not too much time, right? I want you guys to try to somehow formulate the definition slightly differently by using what you learned in 1019, practical logic. Okay, that can also give you another angle to really see how the formal definition can be understood. So math is really your friend, always, to really see something precisely. Okay. All right, so whenever you want to define big O, you got f of n and also the reference function, and then you can also expect to manipulate the reference function by applying some multiplicative constant, which will change its slope. I'm also going to do a visual summary on the example we did very soon, right? But you guys can please take a look at the formal definition, all right, and also the graph. Just remember, whenever you want to show the big O, if you want to say f of n is a member of the family for g of n for big O, that means starting from a certain point, which you have to choose. Starting from that point, the runtime function over here will be upper bounded, which means it will be less than or equal to the modified version of g of n, the reference function. When I say modify, I simply meant you got to apply some multiplicative constant to change its slope. So we're going to reinforce this kind of a definition here multiple times today, right? Just make sure you kind of understand that completely. All right. And then we did, this was the last page we did, which is about, there will be a strategy for you to, how to prove some runtime function of f of n, which normally can be expressed as some polynomial form, right? You kind of sort it from the lowest power, for example, 0 here, all the way to the highest power. Could be 5, could be 6, right? Can be some arbitrary positive integer or even real number, right? So we talk about the strategy being the C can just be the summation of the absolute value for each multiplicative constant. We're going to do more example today, right? We'll get there. And after that, for most cases, the M0, you can safely say that is 1. However, when I say most cases, that means there will be some exceptional cases, in which case you have to verify yourself to make sure 1 is really the starting point for the upper bound effects. If it is not, then you cannot say 1, right? Especially when log is involved. But we'll get there a little bit later today. Right? I promise I'll get back to this remaining part of the proof just for completeness, but a little bit later. Okay? I want to talk about some other stuff first. All right, guys, any question from last time? All right, if no, let's now continue. So the first thing I want to do, let me just see, okay? Let me do a very quick visual summary just about the big O, right? So that one will be, it's more like instantiating nicely the formal definition for big O. After this summary, I'm going to ask you guys to try to formulate the definition in a slightly different way. That can also be a nice exercise to do. All right, let's start with this first. So if you remember, the conclusion was, so let me just show you the slide. If you look at slide number 25, right, from last time, we decided that am plus 5 over here, let's say that's our runtime function. And that one there, we prove that it is big O of n, all right? And then we say that starting from 5 over here, the upper bound effect will be present, all right? That's what we said. And now I would like to just go deeper, to visually summarize what's going on over here very quickly. All right, so now let's take a look. There are 3 functions over here. So we got f of n. So this is a runtime function that we have. So this is, let me make it a little bit thicker. This is our runtime function for some algorithm. Okay, let me just annotate that. So this is some runtime function of some algorithm. And then I want you to take a look at g of n itself without being manipulated just yet. So look at this function here. This is g of n. Okay, so g of n over here is the reference function. And one thing that's very important for you to see right away is if you only compare f of n and g of n. Let's see here. So if I try to just box them, only look at f of n and g of n. Okay, you can see that it is not the case at all that f of n is upper bounded by g of n. You can see that, right? Because f of n is actually larger than or equal to g of n at this point. It is strictly like a faster or like a higher in terms of its running time. It's not upper bounded yet. So what you want to watch out for here is f of n is never upper bounded by g of n, which means f of n less than or less than or equal to g of n is always false. Right? That's important to see. So if you only look at g of n alone, upper bound effect is not there. However, when we write the notation, we will write something like this. When we write the notation, we'll say f of n, the runtime function, is the big O of g of n. Normally, I'll talk also a little bit more about how you should write the g of n in general a little bit later. So normally, when you write a g of n itself, you don't really include a modified version over here, only the g of n without any change on the slope. For example, in this case, g of n will just be n. All right? So g of n itself is not upper bounding f of n. But to really show the proof, you have to somehow do some manipulation. So this is why we got another function over here that's going to show it. Right? So that's the story. All right, so let me write another one here, which is here. So if you try to look at this function here that's in blue, this is the one that's going to show the upper bound effect starting from a certain point of the input size. Okay? So this is really what we have to look at. So this is the modified version or manipulated version, modified version of g of n that can upper bound f of n from certain point. All right, so that's really the one. And where's the starting point? Well, you can see that's exactly over here. So this is really the starting point over here, 5 over here, right? So what you want to observe is, for this one here, starting from this point and onwards. So starting from this point and also onwards, the upper bound effect is there. The upper bound effects is there. Because you can see, starting from this point over here, the modified version is over here, which is larger than or equal to f of n, right? That's where we see the upper bound effect. But before that, it's the opposite. It doesn't need to be true all the time, just after that particular starting point. Okay? It's there. So f of n is less than or equal to c times g of n. Right? In this case, the c is just 9. Right? So this is a c you have to choose. And of course, one more. And to its left, right? To this left over here, if when it's less than 5, then the upper bound effects is not there. Right? It's a quick visual summary about the big O. All right? Any question? Yeah.
What if like the two functions, like let's say n equals 10 or something, they cross again? How would we know if the two functions?
Yeah, good question. So normally we will assume that, well, of course you got to see the individual function. So you got to watch out. So let's say, I see exactly what you mean. So let's say for this function specifically, after this point here, you can see for f of n, it will grow just like that continuously. It's a fixed trend. And for the modified version, it's also growing this way. So you know that the gap is just going to be bigger and bigger. So you know that upper bound effect will just be there. But it might be individual cases. Let's say if at some point, like this. So we do have the upper bound effect, let's say up to here. But at some point, it simply cross again. If that's the case, of course, that means you have chosen the wrong C or wrong M0. In that case, you got to fix it. Yeah, good question. Yeah. You got to judge case by case, of course. Yeah. All right, if no further question, let's now move on. Okay. Yeah, important visual summary over here, right? Just for you to really see, like for each proof you're actually trying to do about the running time, it's really like an instantiation of the formal definition that we spoke about. And I would like to do one exercise with you very quickly, right? What you have known, what you have learned so far is about this. This is formal definition for sure, right? I'll put it here for your reference. And that's kind of the diagram, right, about the upper bound effects. And now, as a prerequisite, you guys have completed either 1090 or 1019. So you have seen logical operator like these, right? Now, my question is, are you able to somehow formulate this, rephrase this kind of formal definition using the logical operators over here? Are you able to? Okay? That's the question. I'll give you guys, maybe how about that? Let's not waste too much time. I know this is a challenging question, to be honest. But I will let you guys think about and give me some thoughts if you have any, and I'll give you the solution. I'll give you guys a moment. The answer will be somehow you have to use these operators. When I say f of n is order of big O of g of n, how can I somehow use the logical operator? But I'll give you guys one hint just to start with. I can say, if I say f of n is a member of the family of g of n. That will be true if and only if Now, what can you do on the right-hand side? All right. And of course, once I give you the answer, I will expect you guys to really understand that. Of course, spend some time understanding it, and then come to me if you need any help. Okay, how about I take you guys' thoughts very quickly, and then we'll see. Okay, go ahead, please.
For all values of n, f of n is less than 0.
I heard about for all, that's pretty good. However, you have kind of missed the part about choosing C and N0. Somehow that one should be also in your formula. I agree, there should be like a for all. Very, very good.
Oh, so no, there is, right? So for all?
For all, for sure, yeah.
Okay, so for all Fn, there should be, so there is.
Like they exist.
Yeah, there exists. A C times Gn, like such that is less than. Yeah, we're to put that together. So there is, and there's C times Gn such that is greater than Fn.
I think getting there, also not exactly, but I can see the idea. I think if I combine somehow you guys answer together, you're getting much closer. All right, but not quite. Okay, let's now write it out. Okay, let's learn from this definition. I would suggest, let's think about what's the proof strategy like. We should choose a pair of C and N0. So they should exist at least one pair. Right? So we should really start with existential quantification. So there exists C and also N0. So the C and N0 are the necessary stuff for your proof, right? They exist. And then I'm going to put something here for exist. So once I've chosen C and N0, I want to say for every input size N, and then, oh, actually before that, I can even say something. I'll just put it here. Before that, I can say, for example, C should be larger than 0, and also N0 is larger than or equal to 1, right? Yeah, just before the for all, right? That's the constraint we also got. Now, for every N, which you guys already covered, N larger than or equal to N0, right? So we're basically describing this part over here. We're talking about starting from N0 and onwards. So this is the upper bound effects. You can think about it for all, it's really about that part there. All right? And N larger than or equal to N0, that implies the upper bound effects is there. F of N is less than or equal to C times G of N. And of course, you can see that it's a nested quantification. It is really important to see that the C here corresponds to the C we have chosen. And also the N0 over here also corresponds to N0 we have chosen. Right? There exists at least one pair. If you can find that pair, you complete the proof. If you cannot find such pair, then there's no such proof. All right. Question?
To bound it, you have to make sure it's less than or equal to. So what, if, let's say it touches the bounded function at multiple points, I don't know.
It's okay, you know, so here you can see, yeah, so the upper bound effect here doesn't really say it should be strictly less than only. It can definitely be touching. So let's say this. Let's say,
choose the lowest? Would you choose the first point where they intersect?
you gotta choose the first point where the upper bound effect starts. That's what you should do. So here, let's say after that point, as long as you got that upper bound effect always occurring, then that should be the point to choose, the start earliest point. Although, strictly speaking, let's say N0 over here is the starting point for sure, the earliest point. If you happen to choose, for example, N0 over here, it's still like a starting point for upper bound effect. So as far as the proof is concerned, you're still fine. But normally speaking, you should really choose the earliest point. Yeah, good. All right, guys, I'm going to leave you to this nested quantification. That's like a prerequisite you're supposed to know. Think about the math, really kind of dive into it. Don't be scared by that. It's a very nice way to show you another angle about understanding what we're doing. And especially see how this part here corresponds to the diagram that we spoke about. Okay? All right, if that's good. And the next thing will be I want to just complete the proof that I owe you last time. All right, so we already did the case where we got this guy here. All right, and the second part will be very similar. So let me just dive into it, and then we'll see. Right, just for completeness. All right, so now we are doing the second part about the upper bound effects. We already argued the upper bound effect will start at 1. Hopefully that's the earliest point. Now we want to argue that the upper bound effect will still be the case for n larger than 1. That means all the way onwards, right? Never stop. So here we are assuming that n should be larger than 1, right? That's what we are considering, as we said last time. So I'm going to start with that. So I'm going to say f of n as opposed to f of 1. Now, by definition, I'm just going to copy this one here just to start with, okay? It's going to be a0 times n to the power of 0 plus a1 times n to the power of 1 plus all the way to a d multiplied n to the power of d. Right? That's how we start with. And eventually, we want to show that this guy here is less than or equal to the c that we have chosen multiplied by the g of n. Right? Remember, g of n is n to the power of d. Right? That's what we want to do. How do we do it? The insight, which I'll tell you right away, is this. If you think about n to the power of 0, n to the power of 1, also all the way to n to the power of d, would you agree, for example, n to the power of 0 should be less than or equal to n to the power of d? Lower power should be less than or equal to higher power, right? Doesn't matter what n is. We assume that n should be larger than or equal to 1. So that should be the case, for sure. Also positive. So here, this one is also less than or equal to n to the power of d, less than or equal to n to the power of d. Okay, so I'm going to write this more like a lemma. Okay, I'll put star, star, star over here. So n to the power of 0 less than or equal to this, n to the power of 1 less than that, all the way to n to the power of d itself, also less than or equal to itself. Okay, so based on this, we can now say less than or equal to. All right, so here the justification will be star, star, star. So you can refer to it. So now we're going to also factor out all the multiplicative constant, right? So what I'll do is I'm going to say this one here times n to the power of d. Because individually they're all smaller than that, so I factor that out. And over here I got a0 plus a1 plus all the way to ad. Now we are facing a situation very similar to this situation over here, right? So if you refer to the lecture last time, in order to argue that this part here is less than or equal to this part, easy, because we already got it, right? Because a number should be less than or equal to its absolute value, right? The same justification. So here I can say less than or equal to, I'm just going to use star star again. So this will be a0 absolute value, a1 absolute value, plus all the way to ad absolute value. And then times n to the power of d. And that's exactly what we want to argue. All right? Again, let me say, very simple proof and very simple math we are manipulating, but trying to really see the insight from there. That's nicely correspond to what we are doing when we're trying to do proof. Also for this strategy here. All right, any question about this proof here? All right, good. Let's now do one more exercise to practice this proven strategy, okay? So now since we have proved it, we can now safely use this strategy over here, okay? So now let's say in the exam or in the written test, you can assume that we have already proved this proposition or this strategy here, so you can just use it, that's fine, okay? I'm gonna show to you exactly what you can write during the exam, okay? So on the slides, you will see there's another example here, which I'm gonna solve with you. That's the complete proof we have just done. All right, let's now do this exercise together. Okay, this one here. Okay. This exercise here, I already tell you, here should be big O of n to the power of 4. you guys are still learning, still brushing up. So now I'm being nice just to tell you right away, that's what you have to prove. But sometimes you might be only given the runtime function alone, but you got to figure out what's the big O first before you can prove it. Right? Just remember. But that's something we'll do anyway today. All right, how do we prove it? All right. And before we do anything, so why don't we try, let me just show you something here. You might be wondering, why is this big O of n to the power 4, right? That's the highest power. So let me just write something down here just to show you a little bit more detail here. So 5n to the power 4 minus 3n to the power 3 plus 2 and then 4n plus 1 times n to the power 0, right? So basically, I just want to write this out explicitly, all right? So we can see that the highest power is this guy here. That's the highest power, obviously. Highest power. And to estimate informally, you can simply drop all the lower terms. So all these are the lower terms. They can be dropped, and also drop the multiplicative constant for the highest term. So we can say we derive or we guess. Number one, we derive or we somehow guess that f of n is big O of n to the power 4. But it's given to you anyway. But you can also try to convince yourself once more. Doesn't hurt. So part 2 is, that's important. How do we prove it? So in order to prove it, we're going to use the strategy we just proved. Okay? So we're going to say we're going to choose C and N0. Choose the C to be some value and also N0 to be some value. By using this proven strategy, N0, most cases, will be just 1. So let me put 1 just for now, but we need to verify, okay, in a moment. What about C here? A common mistake would just be you simply say 5 plus minus 3 plus 2 plus minus 4 plus 1. You can see all the multiplicative constant, 5 minus 3, 2 minus 4, and 1. Is that correct? No. Remember, absolute values over here, right? Okay, that's a very common mistake. Don't make that mistake. What you want to do is absolute value. All right, and if you can do the math, you will find that 15. All right, you can double check. So we claim that we can prove this by choosing C to be 15 and N0 to be 1. But we need to verify to make sure the starting point for the upper bound effect is really 1. Okay? So what I will do is, let's maybe write something here. We want to verify. So the way to verify is to make sure the upper bound effect happens when n equals 1. So it's going to be f of 1 should be less than or equal to c times g of 1. And what's g? And don't lose the context. This guy here is g, right? This is the g of n, the reference function, right? So what's f of 1? So f of 1 over here, you just got to plug in the number, right? So that's without the absolute value. So it'll be 5 minus 3 plus 2 minus 4 plus 1, right? Just plugging the number into here, right? When n is equal to 1. I'm pretty sure you can do it. And then you can easily show that that one there is less than or equal to, what's C? This guy here, which is 15. 15 times g of 1, n to the power 4, 1 to the power 4, which will be 1. All right. And now, is this true? It is, right? Okay, good. Okay, it's verified. There might be cases where this cannot be verified, in which case you got to choose a different M0. You don't need to modify the C. C can be there, but just the N0 may not be as early as 1. It's possible. Okay. All right, any questions so far? Good, very good. Awesome. All right, let me see. If I'm going too fast, please do slow me down. Quite a bit to cover today. All right, and then in the next few pages, let's now talk about some interesting properties about the big O. Especially, you want to really have the intuition about big O being like a family concept. So there are many interesting intuition or insights you can draw from there. All right, I want to start with the first one. And that one there will correspond to, I believe, the next slide. Okay, slide number 27, we have just covered that. Okay, slide number 28. Okay, let's read it very quickly together, and then I'll switch to visual. So if I say a function f of n, the runtime function, is upper bounded by another function, g of n, the modified version, then we say that it's also upper bounded by all other functions strictly higher degree. That's a little bit formal text, but let me just show you. Visually, it's not difficult. All right. So here I'm saying if I say f of n is a member of the big O of g of n. For example, let's say big O of n. If I say f of n is just a member, for example, if I put a member here, what does that mean? That means somehow the highest power of f of n will be smaller than or equal to the highest power of g of n. In this case, n to the power of 1. Okay? That's what the definition says. But let's now get more intuition. And then I'll also draw some connection to the diagram you have over here. All right? We'll do that. Now we want to somehow figure out, given individual big O family, what should be the members that should exist in the family we want to see. And then we're going to see how to relate different families. So these are two perspectives we want to cover. Let's now talk about individual family. So what should be the function that's inside big O of n? That means all the functions that can be upper bounded by n. Or all the functions whose highest power is actually less than or equal to 1, because this is n to the power of 1. All right? We definitely get n itself. Right? And when I say n over here, it can be n, it can be 2n, it can be 3n, etc., as long as it's linear. So I'll just put n here. All right? It could be n, or it could be anything else? Any other member? I can constant for sure. I would just put 1 here. Or another way to think about this, you want to include all the functions that will grow no faster than linear. Log n, right. All right, log n, very nice. So these 3 are the typical ones, right? By the way, I'm not saying there are only 3 members in this particular set. I'm saying that, so these are the typical ones in there. So for example, for n here, also 2n plus 2, and also 4n minus 3 is also there, just linear functions, basically. And let's now try to connect to the diagram here right away, right? If you think about big O of n, right, look at this diagram, all right? N here is linear. Linear is this line here. So you basically, the family member will include all those functions that will grow no faster than n, which will include n itself, for sure. And also this guy over here, we talked about it last time, is the log. And also this guy here at the bottom here is the constant. Right? So if you're talking about big O, it's about all the functions that will go kind of slower than that. Okay? So that's one insight you can draw also as well. So I'm going to put it here. So you can think about like a vertically, so like that. Okay? So here you can simply think about big O of linear, which is the orange one here, contains all functions growing no faster than n. All right? That's one thing. Okay, that's one family we just talked about. Okay, let's talk about another family, and then we'll try to do a little bit inside comparison. Let me now talk about big O of n squared. I intentionally draw it a little bit bigger, but let's see if you're convinced. Okay, so what should be the typical members there? Let's do the similar enumeration. No faster than n squared. What will be the biggest power I can include? N squared, just itself, thank you. All right, n squared, and then you might be thinking n, right? Let's talk about integer first. How about that? You got n to the power of 1. Also, you got n0, the constant, right? There will be something in between. For example, log n should be as well. Missing one thing. And log n, good. Very good, very good. And log n, awesome. All right, and now did you notice one thing here? Big O of n is this guy here, right? N log n and 1. It was included. Can you see? All right. So somehow, big O of n is contained. Let me say a little bit more informally. I'll get back to your 1019 context a little bit later. I'm going to use some set operator to formally, to accurately describe it. But let me just say contain. It's contained within big O of n squared. That means in order to construct a family for big O of n squared, part of it would be the big O of n, which is strictly less power. All right? And of course, these two do not belong to the big O of n. They're outside, but they still belong to big O of n squared. And if you go back to this diagram over here, right, you can see n squared is quadratic, which is over here, right? So let me just try to draw another line here. Okay, sorry. And for that one there, so starting from here and here, right? So that's the one. All right, you can see it's strictly bigger, right? It will include more function there. Okay, so this one here, let me just put it here. Big O of n squared contains big O of n plus other functions growing not as fast as n squared. Specifically, I want you to look at, for example, this guy here. For example, this function here. Okay, I'll write it down exactly. So if you look at this function here, this one here is the n log n. All right, so this is, it is in big O of n squared. Okay, but it is not in big O of n. All right, very important for you to see, right? All right, any question about this page here? Just about including different members. All right, given this, we are now going to think about how we can relate different families of functions, okay? So what I want to do is, okay, we got to relate the family. Let's say this. I got, let me use the same example. Let's say n and n squared. So I got big O of n and also big O of n squared. Now I try to relate these two sets, right? Individually they're a set. I got options here for you. Option number 1, this. Option number 2, this. Option number 3, this. Option number 4, this. What should I put here? How about this? Give me something that will be correct. This can be multiple answer that will give you correct answer. Yeah, go ahead.
Proper subset.
Proper subset, I agree. However, subset here is also true, isn't it? Right? So these two answers are true. All right? This one and this one, they're both correct. So the way to visualize it is like this. So think about if this is my big O of n, and this is my big O of n squared. All right? Okay, anybody tell me? Oh, both of them are correct, right? Because you can see whatever that's in n, that's also in n squared. All right? For 1 and 2, which one is actually a bit more accurate? Accurate in the sense that it really illustrates more about the reality. Because when you say, for example, when you say it's a subset, that means we're including the possibility that this set here can be just equal to this set. Is it true? Can it be exactly equal? Right? Can anybody try to explain to me why one would be more accurate than the other? That one is testing the knowledge from set theory. Yeah, Robert.
So it can't be bigger because every time you go up a degree, it's like a bigger infinity kind of.
Is it bigger because there will, okay, I'll save that answer there. Okay, anyone? It is true every time you increase the power, for example, if you increase the power from 1 to 2, that simply means there will be something that belongs to here that cannot be upper bounded anymore by that. That's more or less maybe what you're heading to. All right? All right, so that's something I'm going to clarify here. So this one is correct, but it's more accurate. Why? Let's see. Let's now get down to basics just for you guys. Okay? So if I say S is a proper subset, by the way, it's called proper subset, right? Rather than subset. If I say that, I got S over here, and also I got T over here. Let's see. S here and T here. If I got S is a proper subset of T, that means, importantly, there will be a member here I can find, let's say a witness. A member in T, but not in S. All right? This is just set theory in general. If you say that S is a proper subset of T, you're saying that its cardinality is strictly smaller than the cardinality of T. So there should be at least one member, at least one, that's in T, but that member there does not belong to S. Let's now apply that back to our context over here. All right? What does that mean? That means over here, there is at least one member that's here that can be upper bounded by n squared, but it cannot be upper bounded by n. All right? That's something you have to make sure you understand. Right? Let me write it down. Okay? This will be at least a function that can be upper bounded by n squared because it belongs to the big O of n squared family, but it's outside the family for this, so that means it cannot be upper bounded by that. Okay? But cannot be upper bounded by n. Can you give me one example?
So anything n squared?
Yeah, exactly, right? Well, n log n, right? Because as long as it's strictly larger power than n, then we'll be good, right? For example, awesome. Thank you. For example, n squared, 2n squared, or even n log n, right? So these functions, for example, belong to here, but they don't belong to here. That's why it's a proper subset relationship. All right. All right, let me now talk one more thing here. Let me just give you one more example here. One more example. Okay, let's say this. These might be something you have seen in 1019, but you just need to brush up, and also maybe some new insights for you. Let's say this is my family constant function. Right? In that way, I got, for example, 1, 5, and 10, right? Things like that. Constant. And then I got a strictly larger set over here. And that's the linear function. Big O of, let's say, n to the power of 1. Just make it more explicit, right? So I know that big O of n0 is a proper subset of big O of n, right? That's something we just covered. Now, I want to give you a little bit more information about how you can understand why there is such a member that's in big O of n to the power of 1, but not in the constant function category, right? Just want to give you a little more insight. Okay, so let's now just cover this. Let's start by saying this. If you look at this family here, just this one here, the orange one. So this will be the set of functions that can be upper bounded by n to the power 0, constant, basically. That means you can choose a C that can be arbitrarily large to really do the upper bound. All right? And then we say that it's a proper subset because there is at least one member. At least one function that can be upper bounded by n linear, but cannot be upper bounded by n to the power 0. All right, let's see exactly why. The example I want to give to you would be, what about just 3n, let's say? All right, let's look at this example here. I'm claiming that 3n is a function that's in the bigger family, but not in the small family. How do we see that? Basically, it will be the case, well, 3n cannot be in here because there's no way for you to choose a C and n0 such that the modified version of n to the power 0 here can upper bound 3n. That's kind of the process you want to go through. But let me visualize that a little bit here. All right, so let's now think about this. So this is our plot. Let's say f of n, and also we got the n here, right? And let's say we do 3n first. Slightly steeper than just n. Let's say this 3n. Okay, we are claiming that if you got a runtime function 3 times n, there is no way to show that it belongs to the family of the big O of constant. There's no way. You might be thinking, what if I choose a very, very, very large constant and say C times 1? No. I can show you that roughly. Okay? Let's say if you got, let's say, a line here. This will show you the general form. So let's say this one here would just be C times n to the power 0, because n to the power 0 is just a flat line. And doesn't matter what C, how large it is, you will just make it maybe a little bit higher, but it doesn't really matter. The higher here, and there's just another trend that's going to go more than that, right? So there's no way to upper bound this linear function here just by having a large constant. Doesn't matter, okay? You just cannot. Okay, think about this inside here, and then I'm just going to put here. So think about this here. So despite how large, sorry, let me write more properly. Despite how large C is, how large C is here doesn't really matter. As soon as you get an intersection between the two functions to the right, you just don't have the upper bound effect. You just don't. To the right of the intersection, right? So you simply just get C times n0 is less than or equal to 3n, right? You can see to the right, you got C times n0 is less than or equal to 3n. So there's no upper bound effect. It should be the opposite, right? For upper bound effects. No upper bound effects. Right? Of course, you can do some similar reasoning about why For example, let's say if I say I got another bigger set over here, it's actually big O of n squared. Now you can choose one function that's here that can be upper bounded by n squared, but cannot be upper bounded by n to the power of 1. Right? You do something similar. All right? That's something I would expect you to know how to do. All right? So understand this one first before you move on. All right? A final diagram I want to show to you, which is important, a final one. So given this, let's now try to relate all the families together, right? So what you're going to have is basically something like that, like an increasing size of the big O family. So we got this one here, for example, strict subset, proper subset. You'll be less than, you'll be proper subset of, let's say, log n, and then proper subset of, let's say, n, and also maybe n log n, proper subset, etc. Right? And finally, to visualize it, the smallest family we have is big O of 1, n 0. The larger one over here would be the log n, which is here. And then we got another one, which is a linear big O of n. And we got another one, big O of n log n, etc. So now it will be some test for yourself. I might say, give me a member here. Give me a member here. Give me a member here. All right? For that one, you can refer to our discussion. Examples. All right? All right, any question about this? Yeah?
So we won't have to kind of formally by a contradiction if something's not?
Yeah, I would say in some way, what I'm showing to you here is more like a proof sketch about how you can show that. For example, here, this cannot be upper bounded by that, right? You just want to show that there's no way to choose C and N0.
But we don't need to worry about
You don't need to worry about the very formal proof, but don't be too surprised if I ask you to explain or to somehow, justify. In that way, I don't really expect like a very formal proof to like a proof by contradiction, not really to that extent. But at least I want to show some understanding like what I'm showing here, at least. Yeah. Alrighty. Okay, so we're done with that one. We're done with that one. Okay, so let's now do a final property about the big O, and then we'll take a short break. Okay, the final one. And this one is also very important, which is about how you can decide both the correct and accurate bounds. Okay, so you will see on the slides, they also got different example, but I'm going to mention something here. Okay, all right, that's something we just spoke about relating the families. And we want to really decide the bounds accurately. Okay? Let me go back to that diagram, and let me use this particular example. Let's say I got two runtime functions to consider. For example, let's say f of 1 would be 7n minus 2. F of 2, 4n squared minus 3n plus 6. Let's say this is the derivation I have, all right? But somehow, according to the diagram we drew earlier, let me put it there. Let me put it here. So here we got the highest power is 1, the highest power is 2, right? So what I can do is, let's now draw just a few, okay? So here I got maybe n0 and 1 and 2 and 3. Okay. Big O of n3, big O of n2, big O of n1, big O of n0. All right, so now let's locate where they are. 7n minus 2 should be here. Agree? Right? 7n minus 2. Very good. And another one, which seems to be more expensive. This is the quadratic one. So it's going to be 4n squared minus 3n plus 6. So far so good, right? Let me just take this one for example, right? So here I'm saying 7n minus 2, let's say, is order of course, that corresponds to the membership sign, membership operator over here, right? So now, of course, you might just say it's big O of n, right? We're good. Now, question, is it correct when I say 7n minus 2 is order of big O of n squared? According to the diagram, yes, because given that this guy here is bigger than this guy over here, if this one here is already in the smaller one, of course, it's also in the bigger one. From the diagram, obviously, right? Also, it would be also correct for me to say 7n minus 2 is an order of big O of n cubed. Anyway, any higher power than linear will be correct. Also, you can also say big O of, let's say, even exponential. Right? They're all correct. However, it turns out if you only state the order like a big O here just by focusing on correctness without worrying about which one is the most accurate, you might have some misleading result, which I'm going to show to you. All right? They're all correct, but it turns out you want to find the smallest power that can really upper bound this running time function. Okay? This will be the smallest power that can upper bound 7n minus 2. So we say that it's the most accurate asymptotic upper bound. Okay, most accurate is really the phrase I want to point out. All right, so you want to be very clear about when I ask you all the correct bounds, so these are the ones, but only one of them with the lowest power is the most accurate, right? That's the point I'm trying to make. And now let's see, what would be the consequence if I try not to be so accurate, but just being correct? What kind of misleading information can I give to you? For example, let's see this. What could be misleading is like this. All right, let me state the following. I might say f1 of n. I remember f1 of n is over here. I would say it's order of big O of n cubed. And then f2 is, f2, remember, is here. And I'll just say it's an order of n squared. If I just give you this information, can you see how misleading it is? I'm telling you the truth, right? Now, just based on what I'm saying here, you can see when I say one algorithm is big O of n cubed, and another one is big O of n squared, intuitively, you might just choose this one to be more efficient. But it turns out, no, it's not more efficient. See my point here? Upper bound simply means what's the worst case. But when you say what's the worst case, you got to be accurate as well. Otherwise, everything is, to the worst case, exponential. Then you are not really doing anything useful. All right? Misleading because not accurate bounds were given. All right, are we okay with this? Okay, good. All right, that's also important, very practical, right? You want to make sure, just if I only tell you big O of the two algorithm, may not be enough, right? You gotta be asking, are you given the most accurate bound possible? That will be the question to ask, right? To make sure. All right, a final thing before we take a very short break. Final thing. And this is something just to point out why you should really write and not to write, right? Okay, let me just see this one here. Do I have the example here? I think I do. Okay, I'll write it down here. That's also on the slides, so I'll just give you another example here. So if I say big O of 7n squared plus 4 and minus 2. All right, this is something you should really avoid writing. Whenever you put, well, thinking this way, if you're putting that there, this is like a g of n, but g of n should be just the function, just the n itself, without any multiplicative constant or lower term. Right? So that's something you want to avoid. Okay, try to avoid. What you really want to write is something that has already been filtered out, the lower terms and also multiplicative constant, right? So what you really want to write instead will be n squared only, okay? Always drop. Always exclude, how about that? Exclude lower terms and multiplicative constants. Okay, so write that one instead. All right, that's all a small point to make. All right, any questions so far? We're good? Okay, so why don't we take a short break and then we'll resume. Okay, we'll take attendance today. How about that? All right, so now I just want to go over some examples about proving and deciding the upper bounds. I got 5 examples in total. I would suggest I do maybe 2 of them. One of them will be the tricky ones. I'll do them together with you. And the rest of the example there, you can also try as an exercise. I'll leave the exercise pages there for you. You can print them out and give a try. The format for the proof will be just similar. Okay. So this is what we discussed right before the break and more example. Okay, let's now talk about it. Okay, let's do number 1 here. All right, so this will be a very typical format for the question you might see later in the test. Okay, so you're given some runtime function, presumably, right? F of n, you know, mathematically is a function, but in our context, it can just be like a runtime function. This is it. And part 1, you want to estimate what's the most accurate, right? We talk about accuracy versus just being correct, right? You got to be correct and accurate. What's the most accurate asymptotic upper bound, big O? Part 1. And part 2, prove your claim. And of course, to prove, you can simply use the proof strategy that we talk about, right? All right, let's now start with the first one. Guys, what's your guess? N squared, okay, pretty good. Okay, very quickly, that's good. For part 1 there, just state n squared, nothing else. I will see your detailed proof in part 2. Oh, by the way, for those of you who are not too sure, the highest power is n squared, because we also spoke before, n log n is still lower power than n squared. We talked about it earlier, right? So once you identify the highest power, drop all the lower terms and drop the multiplicative constant here. So you got n squared. So part 1, easy. And for part 2, you basically have to choose C and also N0. And let's say we use the strategy that we proved earlier. So I'm going to choose N0 being just equal to 1. And of course, we're going to verify. Okay? And what about a C? If I want to choose 1 here, then the C has to be chosen accordingly. Right, according to the strategy. What should that be? Should be the absolute value for the multiplicative constant, right? Here you're lucky they're just positive, right? But you got to remember to also take the absolute value always, okay? So you'll be absolute value of 5 plus 3 plus 2 plus 5. That's what you got to do, right? 5 here, 3 here, 2 here, and 5 here, right? That should be 15. And what you got to do is to verify like what I showed you earlier. I'm going to state what you got to verify, but you got to try that yourself, okay? But you got to make sure you also verify the following. You want to make sure f of 1, right? Basically, you're going to replace this by 1, okay? Should be less than or equal to, and the c we have chosen is 15. What's g of n?
N squared.
N squared, thank you. Yeah, that's important. Thank you so much. N squared. That will be 1 to the power of 2, right? Okay, you got to make sure this one holds. But I can tell you that it holds, but you got to make sure you try that, okay? This is also some very important step. So that means the upper bound effect starts at n0. Okay, that's one example here. And for example number 2, I'm going to leave that exercise for you. It will be done in a very similar fashion. Okay, so that one there I'll put as exercise. And for number 3, I'll do together with you. And for number 4, you can also do on your own. And for number 5 as well. And let's now focus on number 3. All right, together. All right, for number 3. And again, 2 parts. All right, part number 1. Big O of what's the highest power? Log n, agree, right? But basically, you're choosing between log n and constant. Of course, log n, right? If you look at the diagram there, log n grows faster than constant. Big O of log n. Well, you can think about drop the lower term and drop the multiplicative constant. You got log n. And let's now prove it. If I want to prove it, I would say I would choose, again, I'm using the same strategy. And then I got to choose, for example, the c will be equal to something, and 0 should be equal to 1. Most cases, not always. And c will be here, absolute value of 3 plus absolute value of 2, which will be 5. And verify. What I want to verify is that f of 1 should be less than or equal to the c I have chosen, which is 5. Multiply by, right? Remember, g of n is log n. Oh, sorry. I already meant to write g of n. Log n. Log n, and in this case, n will be 1, log 1. Guys, what's log 1? 0, good. Okay, I'm so happy. Good. All right, it's 0. And because 2 to the power 0 is equal to 1, right? Just in case you're wondering why. Okay, you want to review that part as well. Very handy. Okay. All right, so now we want to see whether it's going to be true. Well, let's see very quickly. F of 1 over here is going to be 3 times, right? Log 1 plus 2. Right? This is 0. 3 times 0. 0 plus 2 will be 2. Right? Is 2 less than or equal to 0? But you can see 5 multiplied by 0 here, right? No. So you can see this is the case where if you simply tell me you choose c here and n0 here being 1, wrong. Because upper bound effect doesn't really happen from here. All right? That's really why I want to do this one with you. That's why I kept saying the strategy that we prove work for most of the times, except for those cases you have to verify that maybe otherwise. For example, if log is involved, you got to be careful. I'm not saying whenever log is involved, it's not going to work right away. There might be some log cases that will work, but some cases it wouldn't work. All right, this guy here. Upper bound effects not there. All right, good. And this is something I want you to try. So n0 is 1, doesn't work, we know that. So what about n0 being chosen as 2? All right, that one there, you got to verify. Okay, I'll leave that to you. You got to make sure f of 2 is less than or equal to the constant here and log 2. Now, do we have the upper bound effects there? Right? Question. And exercise for you. If the upper bound effect is there, great. Then you can choose n0 being equal to 2. If it is not, increase it by 1 and try another one. All right? You may have to go on with that. Question.
So like let's say 1, 2, or 3, none of them work. We just trial and error. So like
You basically keep trying. But for most of the function you're going to encounter, I think maybe it's not 1, maybe just 2 or 3. Yeah. If I try to be tricky, maybe you got to try all the way to 10 to waste your time. Yeah, we'll see. Yeah, go ahead.
Could you also like solve it algebraically?
Huh?
Could you also solve that algebraically?
You might be able to, but I would say I wouldn't cover that part in this course. If you work out another way that's going to work mathematically, feel free. Maybe show it to me. I'm interested.
Okay.
Yeah, show me during the office hour. Yeah. If I can share with your fellow student, I can share too. Yeah. But I would say for this course, you can just try a few cases. You should be able to do it. All right, I got about 4 minutes. Okay, so now I would suggest we do something that's really important. We have done so much work on math about asymptotic analysis. We are basically done with it right now with all the big O, like a brush up from 1019. Why are we doing all these? Because given some algorithm that's actually written in some pseudocode or Java code, in our case, Java code, you have to be able to derive the big O and somehow prove it. That's why we're doing all this kind of ground stuff. So today, I cannot do many complicated examples. We got 4 minutes. At least we can do a few, just for you to get some feel. And then there will be something I'll leave on the slides. We'll go over on Tuesday next week, but you can also give it a try. Okay? I can tell you that towards the end, it gets very tricky towards the end. But let's get some simple ones. At least you can see why we're doing all this math. Let's start with this. So now we want to determine what's the asymptotic upper bound for this piece of code. Guys, how about this? Without telling me how you derive it, just tell me what's the asymptotic upper bound. The most accurate one.
Constant?
Constant? The same? Okay, constant. Well, to be honest with you, I would say typically, if your algorithm only involves like a selection, no method call, also no loops, most likely constant. Most likely. Okay? So now let's see how we figure it out. Now the task is not really to count the precise number of primitive operations. We are trying to somehow derive the asymptotic upper bound. So this is how I would suggest. Go line by line still. For line number 2, since I can see they're all just primitive operations, just 1. But overall, it's just n to the power 0 by some constant. So I'll just put 1 here. And for this one here, also just primitive operation, relational, I'll put 1 here. And this one here is also variable assignment, also 1. And also max is also primitive, so 1. So somehow, the intermediate work, I can say I want to get a big O, but what should that be? So 1 plus 1 plus 1 plus 1. And then big O of 4, which is 4 times n to the power 0. So the final answer you should really write down is to keep just the highest power and drop the multiplicative constant, right? So the final answer is big O of n to the power 0, or you can say big O of 1, all right? So that's a final answer. Okay, first example. Easy one. How about this guy? Well, this one you have seen that already, right? 7n minus 2. So that should be big O of n. However, let's now revisit this example here again. But now we don't need to be so stressed out about the precise number anymore. Let's see how I would do it. So here, line by line, for this line here, I got this one here, I got also this one here, but I don't need to write 2 because it's just a constant, just 1. And over here, for the header, I know that somehow the loop is actually going to be depending on the input size n. Either it's n minus 1, n or n plus 1. Doesn't quite matter for me because I'm estimating. So I will just put n here. It's more like an n here plus 1 to be precise. But n plus 1, asymptotically, just n. So I can put n here. Right? And this one here, I know that it depends on how many times the loop is going to be run. In this case, n iterations. If it turns out to be n minus 1 iteration, n plus 1 iteration, also doesn't matter. Because each iteration, I'm going to do array indexing. And also, it's a little bit like this. You might be thinking, should I say 2 times n minus 1? You don't need to write that. Because 2 times n minus 1, let's say 2n minus 2. What's the highest power? Just n. So I can just write n. That's something you want to get used to. If you're only estimating, you can be a little bit relaxing about the precision there. All right, so here I'm going to put just this part is going to be executed, just n. And similarly, this one here, also within the iteration, it will just be n. And also this one here, I++ is going to be more than one primitive operation, but it's still a constant. Give me just 1 minute, and then I'll be done. So that will be also n. And the final one here, outside the loop, is going to be just 1. Okay, figure out the answer. Big O of 1, n, 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 1. So like a big O of 1, 2, 3, 4, 4n plus 2. Doesn't matter. The highest power is simply n. So that will just be big O of n. That's the answer. All right, give me 10 seconds, please. All right, so before next Tuesday, try to take a look at this one here. All right, contains duplicate, which got the nested loop, and also another one here about triangular sum to see if you can figure out what the running time should be asymptotically. All right, I'll see you next week. Don't forget your assignment number 1 is due pretty soon.